Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this following theorem. It is called the squeeze theorem, and it is extremely important. So let's say we have functions g, f, and h, which satisfy the following relationship. F is less than or equal to h, which is less than equal to g, for all x in some open interval I, except possibly at some point a, which lives inside I. And if, then the theorem says, if the limit of f as x tends to a, the limit of f of x is equal to L, and if the limit of g of x as x tends to a is also L, then the limit as x tends to a of h of x exists and is also equal to L. Okay, so we will not prove this rigorously, but it is useful to discuss what it means. So let's say we've got an interval, open interval I, like so, and we've got a like so. What this says is, let's say L is over there. So what this says is, if we have some function h in between two other functions, so for example, we've got a g that looks like that, and an f which looks like that. So if g is over there, f is over there, and we've got an h which is always in between these two. And the limit as x tends to a for both g and f are both L, then the limit of h is also L. So what is the use of this? The use is, so let's say you've got a over there, and you've got some open interval containing a, and you've got some very wild function who you want to prove has a limit of L at a, and this is a very wild function. You have no grip on it. If you can show that you have there exist simpler functions which, for example, are smoother, or that you have a better grip on g, and f bounding h from below on this interval, and you can show that the limit of f is L at a, and f bounds h from below, and g bounds h from above, and also has limit L, then by this theorem, the squeeze theorem, the limit of h is also equal to L. So this saves you from having to use very sophisticated methods to study very wildly behaving functions. So h can be very wildly behaving, but if you can bound him by simpler functions that behave nicer, and which it is much easier to show, to prove that their limit is equal to L, then you don't have to go through all the trouble for h. Okay, so the notes prove this theorem directly, but you can also use our previous theorem to prove this. And you can think of how you should do that. If you look at the statement of our previous theorem, assume that f has limit L, and G has limit M, and for all x in I, f is less than or equal to G, then the limits satisfy the same relation. So you could think of how to apply this theorem that we had before to prove the squeeze theorem that we have just stated. So I will leave that as an exercise. Okay, I will see you in the next one.